we can have informal chats later on. I want to get a certain amount of the lectures done so I know the pace is properly set. Then we can relax a little. Optical density is a measurement that used to be done when we had images on films. It's not relevant much nowadays, but film is still used in some high-resolution imaging applications. So the optical density measure is related to the attenuation of light passing through a medium or reflected by a medium. Could be film, could be anything. You send a beam of light there and something is reflected back. The ratio is the optical density of that for reflection. For transmission, it could be something, you want this to be clear. Is it really clear? Send light through this, and if all the light you put in is coming through, then there is no attenuation. So this is a measure of attenuation. So the value of a pixel, picture element, may be expressed in terms of just a value, quantized 0 to 255, but then in medical images, that value is related to something else, as I mentioned, density, X-ray attenuation. So a physical attribute, such as temperature, if you measure using a thermal camera, density, measured using ultrasound or X-ray or something, or X-ray attenuation coefficient, which is related to density and the frequency or photon energy of the X-rays. The intensity of light reflected from some body or object at the location of that. So I send a beam there, a laser beam, and something is reflected. Measure that in and out. Or the transmittance or transmittivity, if it is a medium through which you are sending light, such as when you are looking at some object, some specimen under a microscope. You may trans-illuminate the object, could be film, could be some tissue, or you may measure by reflection. So all of those are measured in terms of optical density, the log 10 of input to the output ratio. So you need to measure the energy of whatever beam you're using. A perfectly clear spot will transmit all of the light that you put in, so the optical density is 0, because there is log there, log of 1. A dark spot that reduces the intensity of the input light by a factor of 1,000 will have OD equal to 3. X-ray films were specially designed to have, for mammography, optical density 0 to 3.5, very dark, to clear. But of course, it's not 0. Any medium, there will be some attenuation. It's almost clear, perfect. But is it 0? It could be 0.00 something. 3.5 is really dark. For mammograms, that dynamic range is required. So depending upon the part of the body or the type of the object you are imaging, you need to have a certain dynamic range of operation. So that's how you measure it. You don't need that. So what is dynamic range? It's maximum to minimum, or maximum minus minimum. Or you can say minimum to maximum, some range you specify. So X-ray films for mammography, 0 to 3.5 optical density. We don't use CRT monitors. These notes are from the first edition of the book, which I wrote more than 20 years ago. We are working on the second edition, and then these things will go away. There are no CRT monitors nowadays, but you need to have a good dynamic range of the display, the amount of light that comes out. Used to be measured in candelas per meter square, 0 to 600 or 1 to 1000, but nowadays you get much better with solid state or LCD, LED displays. Now they're not solid state, but anyway, those displays are better than the old cathode ray tubes. But when we had cathode ray tubes, we had to be careful about these parameters. So when you acquire an image or display, the device that you're using has a certain range of operation related to the input and a range of the output it provides. And the curve in between, which is not typically linear, it has a certain slope in the linear portion that is known as gamma. And that's an important characteristic of the device you're using to acquire the image, or the device or object you're using to print or make a copy. I'll go to that plot here and explain. So this is known as the HD curve. Here you have log of exposure, that is the input. Exposure is amount of light, X-ray photons, whatever you're putting in. And this is the output on the film or the device in terms of optical density. It could be something else, pixel value, whatever. But this is output, this is input. There is a range where you put some input, nothing comes out. And that is a background level which contributes to noise. For all of this input, the output remains the same, not zero. So that contributes to bass or fog or noise, dark current in CCDs. So there is some output. And you have to overcome that before you see variations related to the input, and then the output increases. And there is a linear part, hopefully. You want that to be linear, and you operate in the linear portion, and then there is saturation. So beyond a certain input, the output remains the same. So all objects have that. And some biological systems, we also have some curve like this. For a certain amount of input, I may not react. And then I have some reaction, and beyond some level, my reaction will stay the same. This slope is known as gamma. And device A has a high slope. It gives you high contrast. But then the range of operation is small. The dynamic range or latitude is small. Whereas device B has a larger latitude. It can work from here to there in terms of the input range. But the contrast will be poorer. So you sacrifice one for the other. You want latitude or dynamic range, or do you want contrast? So you design or choose an appropriate medium. So what is contrast now? There are a few different definitions of contrast. You compare the value, there's some distortion, it's not a circle. So when we talk about shape analysis, you should bear in mind that is supposed to be a circle, but it's some distortion there. There are some different definitions of contrast. Essentially, you're comparing an object with something else, background. And for that reason, it is called simultaneous contrast, because you're comparing two things, not just one. So this is a foreground object. You make a measurement. The value of that is F in terms of optical density. The background, you can take the background to be immediately around the foreground, or it could be somewhere else there, wherever. Or the whole image. It's up to you. Sorry. Okay. So it depends on where you choose the background, but let's take this. If it is already normalized in terms of optical density is normalized ratio. So then you just subtract the two. Easy. So if FOD, if optical density, this is darker, then it is positive. But it depends which unit you use. Another definition is F minus B over F plus B. F is foreground, B is background. The difference and ratio to the sum of the two, or the difference ratio to only the background. So there are two definitions. So both are known as simultaneous contrast. The larger the difference with reference to the denominator, the higher the contrast. This could be positive or negative. If F is darker than B in pixel value, then it will be negative. If F is greater, brighter, then it will be positive. The problem with this is what happens if B is 0, then it's infinite. Or if B is very small, it's very large. So it is unbounded. Whereas this is bounded. Both can't be 0. Then you have 0 over 0. Otherwise, it is limited to the range plus minus 1 or 0, 1. So that is simultaneous contrast. Like water? So, some examples. So here is a test object. These two values are the same, but because the background is different, you perceive them to be different. You don't see them as equal, this and that. This is on a lighter background. This is on a darker background. So the background affects our perception. And that is because our system, the human visual system, is a bandpass system. It's a bandpass filter. So there is a differentiation operation inherent in this. And the differentiation is f minus b. So one of them on the left is 130 minus 150 minus 0.133. On the right side, the same square, the same value, 130, but the background is 50. It is plus 1.6. So the simultaneous contrast of these two objects is different. This is positive, this is negative. So this looks like being dark, that looks like being bright. And that is an important aspect in analyzing medical images too, as to what is darker and brighter and what is the contrast, and how is the background affecting your perception, either visually or in a computational algorithm also. So bear in mind that these apply both to the human visual system of the analyst or radiologist who is looking at images, or if you're writing a computer algorithm, the same thing applies. So there is a concept known as just noticeable difference, or JND. What is the smallest difference between the object and the background that will permit you to see that thing? If the difference is 0, then there is no object. And then how much is required for you to say, yes, I can see that object? There is Weber's law that says JND is almost constant at 0.02 or 2% over a wide range of background intensity. Of course, if you increase the light, you will see the difference. But there is a range of operation, and for a large range of the light, that is the background, the difference between the background and the object should be at least 2% for most of us to be able to perceive the object. And that is in terms of this f minus b over b. So we have here another test image I created. There are 5 bars. Most of you should be able to see this. Some may not be able to see that. That is exactly, that's close to the JND. These values are 155, 175, 195, 215, 235 on a background of 150. So the first one, 155 minus 150 or 150, is about 3%, a little over JND. So most of us can see that. I don't have the other image I created later. If you add noise, then there is a different issue. If you add noise to the whole image, noise will affect your perception. So there will be some level of noise where you will not be able to see this. In this case, there is no noise. So how does it matter? In terms of calcifications in mammograms. Calcifications are deposits of calcium in the breast. Breast tissue is soft tissue. Calcium is harder and will have higher attenuation, so will appear brighter. But then a mammogram that is taken, the breast is compressed, and then X-rays are passed through, and there is a detector. Nowadays it is solid state. It used to be film. But the rays pass through the breast and will be integrated along, the effect is integrated along the path of propagation. So you get a 2-dimensional projection of a 3-dimensional body. So you could have calcifications here, some other tissues there, some other tissues there. And when you project it, if those other tissues are also of high density, then the calcification may not be visible. Whereas a similar calcification elsewhere, if it is superimposed with fat or low density tissue, then it will be clear. Next time we should get, do you have a control for this also? Not now, we'll do it later. We can do it later. Could you turn this light off, please? Here? The other one can stay. So here we have a part of a mammogram with many calcifications called microcalcifications. The size of this image is, the width is 32 millimeters. You see all these bright spots. When the bright spots are on a dark background, low density or fatty tissue or fat, you can see them with good contrast. When they are projected in combination with high density tissue, they become harder to see because the contrast is reduced. There's good contrast here. They're not similar. That and thus the calcifications are not identical. So I cannot say compare that with this, but there is good contrast here. I can see all of these. There it becomes difficult. So the background of an object determines its visibility. The contrast between the two is important. So if that contrast is not enough, and if the difference is above the noise level, then you can enhance it. We will talk about some enhancement algorithms. To represent the variation or variability of the information in an image over its full range, earlier we said dynamic range, but that only gives you one number. It varies between 10 and 240, but that's just a range. To give the full information, you make use of the histogram. Dynamic range is only global information, but histogram gives information on the spread of gray levels over the dynamic range of the image. Is it uniformly spread or does it have some shape? Is it Gaussian? Is it unimodal? Is it multimodal? So the histogram, if you want a complicated mathematical equation, the probability of the occurrence of a gray level L is the delta function Fmn minus L. The delta function is equal to 1 when the argument is 0. But that's more complicated than needed. You simply count how many times 0, 1, and so on occur in the image, make a plot, that's the histogram. If you integrate that, you will get Mn, the number of pixels in the M by N image. But that is the histogram. Now normally usually we normalize it. With the lowercase p is the PDF or the probability density function, approximately. The probability, the number of pixels counted, p divided by Mn. And then the sum of this PFL is equal to 1. Now this behaves like a probability density function. Now you don't get the probability density function by taking the histogram of one image. You cannot call it a PDF, but if you have a large collection of images of the same type, then you can average them. But they must be of the same type, like mammograms only, CT images only, CT images of the head only, CT images of the head of pediatric patients, men, women, population, various populations. Then you average them, the individual histograms, normalize them. Then you can say I have an estimate of the PDF of that category of images. And that is useful in designing appropriate optimal filters and data encoding and other techniques. So the basic histogram gives you some information, but it is useful in many other applications in understanding the nature of the signal. So here is an image of a myocyte, one cell of the heart muscle of a rabbit from a video image, so the quality is quite poor. The histogram is that after digitization of the video signal. The dynamic range is 0 to 255, but it's not occupying that range. That's the image I got from my colleague in the neurosciences. You can see that the probability of occurrence of all these values is very low, and bright values are almost not existent. The image is very dark. So this is where the real information lies. So the histogram tells you about that. Are you using the range properly or not? So here is an image of collagen fibers in cross-section from the knee joint ligament of a rabbit. I'll show you some examples based on this later on. Some of these imaging methods are described in the first chapter. So if you haven't read that, please go through the first 150 pages or so of this file. Just a story, you can quickly read that. So you see sort of dark objects on a light background, but they're not all of the same value. So you see a histogram that is bimodal, 2 modes. But because there is noise, we see some variation that is artifactual. When I average the image using an averaging filter, you see the 2 peaks clearly. The objects are dark. So this part belongs to the dark pixels, the collagen fiber cross-section. This is the background, brighter. So if you want to define a threshold to detect the objects, you would want to find some point here between the peaks. But they are overlapping. If you had one mode here, another mode there, you can easily separate them. But here they are overlapping, so you will mix background and the object by using any cut point here. But at least now you know the cut point or the threshold must be somewhere there. So here is a part of a mammogram that I showed earlier. That's the tumor. This is rest of the mammogram. This is only 700 by 700 pixels out of a 4K by 4K image. The width is 62 micrometers. 44 millimeters. The pixel size is 62 micrometers. We had a lot of difficulty in scanning films. We got a very high resolution camera, 4K by 4K pixels. At that time, in the 1980s, that was big. Now you get that in a cell phone, you get even better. But at that time, this camera had one 4K array, and then it was translated inside the camera. And we had to keep the film on a light box that was specially designed to be uniform. And that was put on a suspended air table, very heavy table, but suspended. But we were on the 4th floor. So in spite of all of this, if somebody walked, that stepping of that CCD would be affected, and we would get artifacts. So at that resolution of 50, 60 micrometers, one has to be careful, and we had to take many precautions. Now all of that is obsolete. The histogram of that is here. This is multimodal. The first one was almost unimodal. The second was bimodal. Now we have 1, 2, 3, 4, maybe 5 peaks. Depends on how you define a peak. So this is all dark background. This is the medium density tissue. This is higher density tissue, higher and higher. If there are calcifications, they'll be somewhere here. This is the range 0 to 255 after scanning. This is the probability now. The histogram has been divided by the total number of pixels, so this is the probability. But that is from only one image. So this is a CT image of a patient with neuroblastoma with a large tumor in the liver, near the liver. The liver has been pushed, the kidney has been pushed by the big tumor. This is one section. The liver and kidneys have some intermediate Hounsfield units. I said 50, 60, 70, most of the abdominal organs. The bones are of higher density. This is the bench of the scanner. So forget that. Spine, the spinal canal, aorta, and some of the blood vessels. The tumor has calcified tissue. After treatment, or the body naturally fights the disease and causes calcification, or when the patient is treated, the cancerous tissue will be killed and it becomes scar, and then it becomes calcified, high density. There is low density fat, low density medium density liver kind of tissue here, same density. Lower density could be fat if it is near 0 Hounsfield units, or could be even lower than that, or intermediate could be scar tissue. So this tumor has a combination of all these types of tissues. So when you take a histogram of that image, you get this, again, multimodal. This is Hounsfield units. 0 is here. This is water. Negative fat here. If there is air in the stomach, then there'll be minus 1,000, minus 800, and so on. but I'm cutting at 200, minus 200 to plus 400. So calcification is somewhere there. Not as hard as bone. Pediatric case, so the bone will not be very hard. Adults' bones may be 800, 900, 1,000 Hounsfield units. Pediatric maybe 400, 500. And the calcification will be somewhere there, 200 to 400. This is the histogram of the entire scan of the patient in 3D, all these slices. You get a better histogram. Now it is spread over a wider range. Now you can see the peaks more clearly. So these are all the abdominal organs. This is perhaps the cancer tissue of higher density or attenuation. This is calcification spread over various values, 200 to 400. Minus 100 will be fat and air combined. And it goes further down. If you have the chest portion, then there will be minus 800 maybe. So that's what this is again a multimodal histogram. So when you have histograms like this, you have to design appropriate measures to characterize them. Mean and standard deviation will not work all the time. Skewness and kurtosis will be useful in many cases and maybe higher order moments. Okay. When you have the PDF, then you can derive some statistical measures of information, statistical only. Information is characterized in the statistical sense in terms of the probability of occurrence. If some event has a very low probability of occurrence, you don't expect it, and when it happens, you're sort of surprised, and that is a kind of information. I looked at the news in Calgary. It's February. The news said it's very cold, minus 40 degrees. Okay, well, I'm here. I'm happy. It's minus 40 degrees there. But that's what happens in February. So it's okay. If I come here and if it is minus 20, then that's a shock, and that is information. If you say it is raining here, I say, okay, it rains always. If you say it is hot in Mandayam, it's always hot. My uncle used to say, Mandayam has 3 seasons, hot, hotter, hottest. So information relates to probability. When something that has a low probability occurs, there is information. Something with probability equal to 1 or near 1 doesn't convey much information when it happens because you already knew it. So in an image, you consider each pixel to be a source of information, which is a little strange, but that's the way it is in statistics, by a discrete source of information with gray levels as it states. And then there are L gray levels. You take the probability of occurrence, PL, for all of them, and you consider the gray level value to be a random variable, and a measure of information is conveyed by statistical uncertainty. It has nothing to do with the structure or the semantics of the image, medical or calcification or tissue. There is no such connection. A measure of information is expected to meet these conditions. If P is some source of information, the value H of P should be continuous for P between 0 and 1. Continuity is a requirement. HP is infinite for P equal to 0. HP is 0 for P equal to 1. This is what I said. If something with a probability of 0 occurs, you get the maximum amount of information. If something with a probability of 1 occurs, there is no information. HP2 is greater than HP1 if P2 is less than P1. The lower the probability, the higher the information when it occurs. If 2 statistically independent image processes or pixels F and G are considered, the joint information HFG is HF plus HG if they are independent. If there is dependency, then it will be less than that. So these requirements are met by the log function. And because log of a value between 0 and 1 will give you negative values, you put a minus sign. And then you weight it with the probability. Apply a weight equal to the probability. So PL HPL or PL log PL. And sum over all the values, L going 0 to L, capital L minus 1. That is entropy. It is called zeroth order entropy. Some books say first order, but it's actually 0 because you're not considering any neighbors. If you consider one neighbor and take joint, then it is first order. If you consider 10 neighbors, then it becomes 10th order. Because the neighbors are correlated. Right now, you're taking only one pixel at a time. So this is entropy. It is one measure of information. If you differentiate that and do the optimization process, you find that the maximum occurs when all the probabilities are equal. If there are L levels, the probability of each one is 1 over L, and then the maximum value is log L. And it is common to use log 2. Then it is called bits. If you use log 10, it's not bits. You could use any other log, it's just scaled by a factor. But log of 2, log of base 2, then you get in bits. And if you have 8 bits quantization, then the maximum is 8. So please note that entropy is a statistical measure of information. It has nothing to do with what is contained in the image in terms of structure or meaning or application. It's based on the PDF, the probability density function. It is not sensitive to pictorial, structural, semantic, or application or diagnostic information. It does not account for the spatial distribution of the gray levels in the image. The pixels could be anywhere, arranged whichever way. There is no spatial information. You have a bunch of pixels, M by N image. Count how many times each value occurs, and that's all you have. Where are they located and how they are distributed in the image is not there. If you want that, then you must take joint entropy, higher order entropies. It gives a lower bound on noise-free transmission and storage requirements. You require at least that many bits. There are a few properties. HP is greater than 0, equal to 0. Equal to 0 only for p equal to 0 or 1 by definition. The joint information is important. When you have a number of pixels, p1 to pn, and you consider them as n events, each pixel is happening somewhere. Its value is varying somewhere. The joint entropy is less than equal to log of n, where n is the number of those pixels or values you're considering. Equal only with equality to that, only if all of them are equally likely. So now we can define joint information between two images F and G. That is PFG L1, L2. L1 is the variable in one image, F, and L2 is in the other image, G. So the joint probability and the log of that. Now double summation over two variables. If the two sources are statistically independent, the joint PFG becomes PF times PG. Then the joint entropy is also gone by this condition. HFG is less than HF plus HG. But if the two are statistically independent and you get this condition, then it is equal. That's the maximum. So if two images have some correlation, by viewing this and that, you're not getting the sum of the information in the two, because some information is common. You get a little less than the sum. If you get two images of the same patient, or two views of the same object, there is some correlation. So you don't get the sum of the two information measures, but something less. The conditional entropy is another measure that is useful in transmission of images. HF given G. You have already seen G, and then you are given F, another image, related hopefully. Then that is PGL2 times PF given G, conditional probability. and log of that conditional probability. This F bar is, that vertical bar is condition, and that is given by this joint probability, PFG times log PF given G. Now, HF given G is HFG minus HG, because you already have seen it G. So you already have that information. And that is less than HF, less than equal to, because they are hopefully correlated. With equality, if and only if F and G are statistically independent. So this happens in communication. You're sending an image, there is some distortion. Nowadays there is error correction and so on. So usually you don't get any loss in transmission. When you send some data to the cloud and get it back, usually you get the correct data back. But previously there were situations where there would be some loss of information. So then the question is, how are the two related? Then that's a useful measure. The conditional PDF is defined in this manner. I have two now. This one. Okay, this works. Okay. The conditional PDF is defined, just a probability definition here, the joint probability divided by PG, the one that you have seen first, as long as that is greater than 0. Higher order entropy. I mentioned earlier that the first entropy measure we saw, we are considering each pixel separately, the probability of occurrence of various gray levels. Not each pixel, but gray levels. But there was no correlation information taken into account. What's been observed is that many real-life images have the value of H, entropy, much less than the maximum. You use 8 bits. The maximum is 8-bit quantization, 0 to 255 values. The maximum is 8 bits of entropy, but you may get some value that is less than that. But the value in a real-life image is much lower. You may get a value of 4 or 5 or something, but that's not the true information because correlation was not taken into account. Neighboring pixels are not independent of one another. The real entropy is much lower. And how do you get that? You consider sequences of pixels. You take a number of pixels together and look at their joint probability of occurrence. How are these pixels arranged? It's up to you. You can take in a straight line, 1, 2, 3, 4, and so on, or you can take a neighborhood, 1, 2, 3, 4, 5, 6, 7, 8, 9, in a 3 by 3 neighborhood. And then you get various combinations of pixel values, all zeros, 1 and zeros, and 1, 1, 1, and so on, all of those. Then you find the probability distribution function or density function of that sequence for all possible occurrences. And then you find the entropy of that. So if you have L0 to Ln in the sequence of pixels, n is the number of neighboring or additional elements considered, not counting the first one or the 0th one. Then the probability of that string of values, log of that, summed over all such occurrences and normalize 1 over n plus 1. There are a few different definitions of this. It's been shown that Hn is a monotonically decreasing function of n. The more the pixels you take in this string or sequence, the lower the entropy, and approaches the true entropy as n tends to infinity or n is large. So to get the true information content of an image, you should consider sequences of pixels. How you define the sequence is up to you depending on the application. If it is a 1D signal, you consider a number of values in a window. Mutual information is another measure that is important in medical image analysis when you want to compare images of the same patient taken at different times, of the same patient taken using different imaging modalities. How do you put them together? So IF given G, two images F and G, is HF plus HG minus HFG. Remove what is common between them. So the real information is not the sum of the entropies of the two, but a little less. How much is the loss or difference? That depends upon the relationship between the two images or the correlation. It is HF minus HF given G or HG minus HG given F, conditional probabilities. So this represents the information that is received or retrieved. Imagine a lossy transmission situation, as I said earlier. HF is the information input to the transmission or archival system. F is the image, you send it over a data transmission line, and G is what is received on the other side. HF given G is the information about F given that the received or retrieved image G has been observed. If G is completely correlated with F, no noise, everything has come through. HF given G is 0 because G and F are same. So IF given G is HF. The full information is received. No loss or distortion. If G is independent of F, HF given G is HF and IF given G is 0. There is total loss of information. So something happened and you sent this and they got something else. So entropy and mutual information are useful in the design and analysis of image archival, coding, and communication systems, and also in comparing images of the same patient taken at different times and different modalities. The story I say often about this is some years ago I sent a nice magazine from Canada to my parents in Mandayam. And then phone call was expensive at that time. Then I got a letter telling, why did you send me this magazine? Some Soviet magazine, something. They got some rubbish magazine. I said, no, that's not what I sent you. I sent a nice calendar. So somebody swapped it. So that is total loss of information. I sent something, they got something else. So then IF given G is 0. When you acquire images, there are problems. Initially, the lens was not focused, so it was a little blurry. They fixed it. Now it is sharper. Blur is quite common. The patient moves, when you are taking a picture and this person goes like that, or moves a hand, or something happens within the period of exposure or imaging, and there is blur. The blur depends upon the motion, if something is moving, or the patient is moving, or the subject is moving. The heart is moving, of course. So blur is caused, and that is represented as a spread function, spatial spread. Many components cause blurring, such as lenses. The film itself will cause some blurring depending upon the size of the silver halide crystals used, the size of the CCD, the noise. Noise is different, but there are many components that cause blurring. The simplest visualization is the point spread function. Suppose I put one point, take a picture, or I want to write one point, but then the paper is absorbing the ink, so one point spreads over and becomes that big. Then that's a spread function. That is happening over time, but eventually it stops and then you get a blur, a point spread function. PSF is the point spread function. This is 1 pixel, so it is square. It's not a single point, but it is 1 pixel. And then when I apply a Gaussian blur, that's what I get. Blurring functions look like that, but that is isotropic. It is spreading in all directions equally. Bell function. But if the patient had moved in one direction, suppose horizontally, then the blur function would be a line, a straight line like that, or line whichever way the patient moved, the object moved, or the camera moved. So mathematically, it is defined by, an ideal point is defined using the delta function, and we know that the delta function integrates to 1. A few points about the delta function. There are a few definitions of the delta function. One is its action within an integral fx times delta x minus x naught integrated a to b, where x naught is within a to b, then you're getting that value fx naught. So this is known as a sifting property. You are getting one value out of that signal in that range by integrating the product of the function with a delta function in this manner. You can extend all of this to 2D. 1D continuous is good for this illustration. You can also write this as fx is f alpha delta x minus alpha. So what does this say? The interpretation is different. The signal is made up of a number of delta functions, delta x minus alpha, at various positions, x equal to alpha, or alpha equal to x. And the value at each point is f alpha. So then it says it is resolving some signal fx into a weighted combination of mutually orthogonal delta functions. So we can say any function that is going like this is simply a bunch of delta functions and so on. When you put them all together, depending on the position alpha, that is the signal represented in terms of delta functions. So we can, what it says is any arbitrary function fx can be expressed as a sequence of impulse functions, delta functions. Each has its own value according to the value of the signal there. So this is called resolving the arbitrary signal into a combination of mutually orthogonal delta functions. That is, when you multiply this delta function with any other and integrate, the output is 0. So they are mutually orthogonal. Yeah, the delta function is defined in terms of its integrated strength. The integral is 1. We already saw that. There are a few other definitions using exponential functions and so on. Let's not worry about that. I'll skip some of these parts. Feel free to read them in the notes later. The image obtained when the input is a point or impulse function is known as the impulse response, as in 1D system analysis, signals and systems. But in the case of images, it's called a point spread function. Spread happens in xy or xyz or how many other dimensions you have. If you have xyz time, then it is 4 dimensions. Spread can happen in multiple dimensions or not. You may have a 3D image, but the spread may be happening only in 2 dimensions, or maybe only in 1 dimension a long time. In the case of a 4-dimensional image, xyz time. So that's a point spread function. So if you have a linear shift invariant system, in imaging we call it shift invariant instead of time invariant. There is no time here. So gxy, the output is a convolution in 2 dimensions of the impulse response, always written as h, times the input image f. F alpha beta times h x minus alpha y minus beta. Integrate over all alpha beta. And that gives you one value at xy of the output. You can change variables, and you can write this as h alpha beta times fx minus alpha y minus beta. So one of the signals is reversed in that variable, alpha or beta, and then in the other variable, beta, and then multiplied with the impulse response in 2D, integrated over 2D. You get one value at gxy and do it for all xy. So this is convolution. Some books may use double star or put a circle, but we'll just say star. Convolution. I'll show some examples of convolution much later. Some effects of cause of blurring are focal spot in the X-ray tube, if you're talking about X-ray imaging, regardless of the detector. Thickness of screen or crystal in the detector. Solid state detectors also have a certain thickness. And if you're using a crystal to convert X-ray photons to light photons and then you image the light information using CCD, then that crystal will cause blurring. Or in the case of positron emission tomography and single photon emission computed tomography. There is a crystal, a scintillation crystal, that responds to the photons coming in of gamma rays. And the scintillation will cause some spreading within the crystal before it is detected using a photomultiplier tube. There are some examples in the first chapter. And scattering. An X-ray beam, a photon that comes like that, may be scattered and it may go and hit somewhere else on your detector. It's not coming, it would naturally go in a straight line, but if it hits something and then it is scattered, it goes elsewhere. And a number of them going elsewhere will cause a blur. So if you have an ideal point source, X-rays or light, then, if I lift my hand, it comes closer. Okay. An ideal point source, then the object is here, you get the shadow there. But if the focal spot is large, then you get multiple shadows. So you get the main shadow, umbra, and then the penumbra. So this represents blur. The focal spot, by the way, is the size of the spot on the X-ray tube target. You have a beam of high-speed electrons coming and hitting accelerated electrons. And where they hit, then the X-rays come out from that spot. But if your beam of electrons is fairly thick, then the focal spot will also be thick. Then there will be blurring. So that is the effect of the focal spot in your X-ray tube. And you have X-ray tubes regardless of the sensor, so this happens. Now, the spread function may be characterized in terms of a couple of other functions that are related. And depending upon the application, you may get one or the other of them, not all of them, but you can derive the others. Point, line, and edge spread functions. A point spread function is when you have one point, but you can't make an ideal point. If I draw a point, it'll have a finite thickness. Digitally, I can make an array with only one pixel having a large value, everything else being 0. But if you want to take an image of a real object, a very thin hole or very thin spot may not be suitable in an imaging situation. It may not be practical to take a picture of that. Too small. But you can construct phantoms or test objects of other types. You cannot construct a point of no dimension. Impossible. But you can create a line. We can take a tube, very thin tube, fill it with the radioactive material in single photon computed tomography, emission computed tomography. I have a line source. I can take a picture of that line source. It's a tube. It has a certain thickness. The thickness is not 0, but it's thin. But I can't make a single dot of the radioactive material. So if you take a line and take a picture of, or you can take a wire in X-ray imaging system, take a gold wire, very thin. Gold and copper can be stretched to very thin width or thickness. Take a picture of that, you get a blurred line. Then that's a line spread function. A cross-section of the ideal line is a point. If you cut that line, it's a delta function. If you assume the thickness is practically 0. The reconstruction of a cross-section of a line phantom using projections, treating each one as a projection, and going through a reconstruction from projections, CT kind of algorithm, you can get the point spread function. But if the imaging system is isotropic, it behaves the same at all angles, and the line source is very thin, then you can assume all of those projections will be the same, and you can reconstruct an isotropic point spread function using one line spread function, cross-section. Sometimes a line may also not be feasible. Then you can make an edge. An edge is easier, like a perfect edge. Make a block and make this a perfect edge and take a picture. So this is an ideal edge. And that edge will be blurred. And if you take a section of that, then you get a line spread function. take a section of that, you get a point spread function and reconstruct and so on. So there is a relationship between these. And depending upon your imaging system and what you can make as a test object, you can go from line to, delta point to a line to an edge. So point spread function, line spread function, edge spread function. Depending upon which one you get, you can get the others. Usually, in practice, you would do either this or that and work backwards to get that. So if you get an edge spread function, my ideal edge is that, but what I get is this smooth, blurred edge. That is taking a section like this of the edge. So this is now a spread function of the edge. The point spread function may be estimated from the line spread. The derivative of the edge, going back here, the derivative of the edge spread gives the line spread. So if you take the derivative of this along x, of the ideal, it should be just an impulse. But now it's blurred, so the derivative will be something like a Gaussian function. So coming from the edge to the line spread is just a derivative in that direction. So line spread FLXY is integral of the delta function, and you separate the delta xy to delta x delta y, and then take the delta y out because we're considering the x-axis, integral along the x, that's delta y. This notation is a bit, I would say, awkward, but I've checked it with my colleagues and it makes sense with this illustration. Separable functions, yeah. That's the assumption made here. So this separability is the assumption made. Delta y is over the 2D, delta y over the 2D xy space is a line function along the x-axis. That's the notation used. Now the line spread function HLXY is the impulse response H alpha beta in 2D convolved with the image FL. That's the line image. Or you can shift the other way, they change the variables. That turns out to be H alpha beta times delta y minus beta. And that turns out to be integral of H alpha y, and that is integral on the x-axis of hxy. So when you get the line spread function, it is an integral along one axis of the two-dimensional point spread function. So this is a projection, like in computed tomography. So if you can do this at various angles, you can capture line spreads at various angles. So you place your edge at different angles and obtain multiple images and take this, get the line spread. Or if you have a tube, a line function, place it at different angles, take multiple pictures and combine them. Put them in a reconstruction algorithm that we will not be seeing. It's in a different chapter, but go through a reconstruction algorithm, then you can get the point spread function. If you take the Fourier transform, capital H is the Fourier transform of the small h Ly, exponential minus j2 pi v, 1D Fourier transform, and go through this, get the dy out, and take the HL and write it in this manner, and write it now as a two-dimensional integral, because we want to relate it to the two-dimensional point spread function. Exponential minus j2 pi ux plus vy, but now u equal to 0 axis, because we are only taking one line spread. That integral turns out to be huv at u equal to 0, which is h0v. So you're getting the values of the Fourier transform of the two-dimensional point spread function along one axis, one line. And if it is isotropic, you take that and write at all angles, using the polar coordinates, and you get the two-dimensional Fourier transform. You take the inverse transform, you get the point spread function. So this is the Fourier method of reconstruction from projections. Okay? I'm mentioning this, but if you want to confirm it, please go through the notes and make the derivations. All the details are there, but you may need to work out the steps. So HUV is the two-dimensional Fourier transform HXY, which is known as the modulation transfer function. Some authors call it modulating transfer function, but it's the correct terminology is modulation transfer function because the input is modulated by this in the frequency domain. So the Fourier transform of the line spread function gives the values of the Fourier transform of the point spread function along a line in the 2D Fourier plane, in this case along the V, the vertical axis, because the line was in the horizontal axis in the input. If you integrate that, you get the edge function. Integrate the line, you get the edge. So Fexy is integral beta going minus infinity to y of FLX beta. And that can be written as integral of this delta function. Because a line, if you take a section, is a delta function. So that edge has this property. As I said, it is 1 here and 0 there. That's the edge function. So the edge or step function is obtained by integrating the line function. And the edge spread function is given by integrating the line spread function. Or the line spread function is given by the derivative of the edge spread function. So they're all related. So if you cannot make a point source, if you cannot make a line source, make an edge phantom. Take a picture of that, take a section, line spread, reconstruct the point spread. So the Fourier slice theorem says the Fourier transform of a profile of the line spread function is equal to the radial profile of the Fourier transform of the point spread function at the angle of placement of the line source. That's the Fourier method of reconstruction from projections. If the imaging system is isotropic, that is, regardless of the orientation of the object, you get the same image with the corresponding rotation, then one profile is enough. One line spread is enough. Then you rotate that and get the two-dimensional Fourier transform. An inverse 2D Fourier transform gives the point spread function. So we did that using the gamma camera in emission computed tomography. So this is my PhD student made this line phantom. The line phantom is internal radius of 1 millimeter filled with 1 millicurie of technetium, and an image was taken. There is noise, and this is the spread. The line is supposed to be 1 millimeter, but the pixel size is 1.56 millimeter. So because the pixel size is bigger than the line thickness, we can assume the line to be an ideal line. But we are getting a blur here. This is only 64 by 64 pixels. This was done a few years ago, but SPECT images have very poor resolution compared to X-ray images and CT and MR images. SPECT images nowadays may have more, maybe 256 square, but not 1K by 1K. No. So the width is 100 millimeters of this image. The pixel size is 1.56 millimeter. If I take a section that is this way, I get that, almost a Gaussian. If I average over all of these, it was supposed to be vertical. It's slight displacement. I didn't correct for that. The average is, wait, let me see. Average is a solid line. The single section is this dotted line. You see some variation there. So when you average, there's also a little bit of angular variation. We get this. So we will take that to be the line spread function. And from that, we computed the point spread function and the modulation transfer function for different source to collimator distance in SPECT imaging. So there are practical applications. I'll show you one more later on towards the end of this chapter. So these things are important in practice. They are not just equations in the book. They're all used in real life. So I've been talking about resolution, pixel size and number of pixels, 64 by 64, 256, or 1000 by 1000. But resolution is expressed or could be expressed in many different forms. The sampling interval, in millimeters or micrometers, what is the size of a pixel? It could also be sampling interval in terms of your detector, CCD, what is the size of each CCD and what is the spacing between them. And if you're using a laser beam to scan, what is the thickness of that laser beam? If I use such a big laser beam, then the pixel is going to be big. I can move the laser beam 1 millimeter at a time, but if my laser beam has a thickness of 10 millimeters, it makes no sense, right? So you cannot just say how many pixels I have. How did you get those pixels? And what was the probing method? What was the thickness of that probing beam if it is like a laser beam and you scan? And the sampling or the displacement of the beam must be done in accordance with the size of the beam. The width of a profile of the point spread function, called full width at half maximum. That is, in this case, the clinical practice is to specify, this is the maximum, 170. So take half of that, 85. What is that width? It is called full width at half maximum in SPECT imaging and nuclear medicine imaging. Millimeters. The size of the laser spot, as I said, what is the diameter or radius of that? In typically micrometers. If you're scanning a film or you're scanning some object. The smallest visible object. Now these are related to the imaging process, image data acquisition. Suppose all of that has been done and you are given a picture. So what is the smallest object I can detect? 1 millimeter, half a millimeter, or 1 centimeter? So that will be in millimeter or micrometer. The finest grid pattern that remains visible, that is separation. Two objects, if they are too close, they will appear to be one. So what is the minimum separation that I can detect? Or you take a grid pattern like a wire mesh, take a picture, and take a picture of different wire meshes at different spacing. As the spacing between the wires becomes smaller and smaller, eventually it will be just one big blur. So what is the finest spacing grid in terms of line pairs per millimeter or spacing in millimeter? If you do this, it is millimeter inverse. These are all millimeters or micrometers. So X-ray film was previously quoted in terms of line pairs per millimeter. So line pairs, meaning your test object has lines. Take lines and then very thin separation. So how many of these pairs of black and white, a wire and no wire, will give you black and white? So what is that line pair per millimeter that you can detect? This is possible, but eventually when you have very thin lines, they will all merge into one blur. So that is line pairs per millimeter. Screen film combination, when you put a screen which is a fluorescent screen to convert X-ray photons to light and then a film to capture the light, there is blurring by the screen, or in the case of SPECT imaging, SPECT is single photon emission computed tomography. And PET is positron emission tomography. When you have a crystal, scintillation crystal, sodium iodide, that introduces blur within the screen or the crystal, and thicker the crystal or the film, the screen rather, the worse the blurring. So when you introduce that, You may go down to 5 to 10 line pairs per millimeter. In mammography, 20 lines per millimeter is what is required or specified as the required resolution. Computed tomography, when I wrote this book, it was 0.7 line pair per millimeter. Nowadays, it is better. Microcomputed tomography can give you 10 micrometers. Nowadays, maybe 5 micrometers. And SPECT is very poor. 0.1, like 1 centimeter. Okay, let's take a little break. Any questions? Any comments or questions or doubts? We're going to change the topic a bit now. Images will come later. Pictures and stories will come later after all the equations, and there'll be more equations later. Everything clear? Okay. Please do go through the notes and the equations and work them through later on. We were talking about having a test quiz or something. We don't know yet about the format. If you have any suggestions, concerns, please talk to Dr. Raghavendra or Dr. Narasimhadhan and let them know what kind of a test or quiz you would want or not want. It's up to them. They are the organizers. I'll just talk. And if he says give a test, I will give the test and the solution to him. If he says make it difficult, I'll make it difficult. If you get the book, at the end of the book, each chapter, I have a number of exercises that I used to give my students, and you may go through them if you're able to access the book. By the way, these notes, I had to get permission from CRC Press, and they asked me, I previously had this anyway, they wanted me to put the copyright symbol and say it's only for you and not for public distribution. So it's only for you. Okay? So let's look at, what's that?
If there is a shared material, you share some PDFs.
Yeah. This is the file I gave you.
Shared with them.
Yes, only for you, that is. Not to be shared further. That's what they have told me, so I'm mentioning that. And don't buy this book because the second edition will come next year. But this book is 20 years old. The equations are the same anyway. So let's look at the Fourier transform in 2D and some examples. The first question is, why do you want to do this? Why do you want to go to the frequency domain? You have an image, why transform? You want to assess the spectral content. You want to assess the energy distribution over frequency bands. How is the energy spread? Not in terms of gray level, but in terms of frequency. And we will look at what frequency means. If you want to design filters, you need to know the bandwidth of the signal and noise, which part you want to conserve and which you want to reject. To remove noise or enhance. To enhance, you need to know which band is of relevance in terms of the details of interest. Extract certain components that may not be separable in the image domain or the time or space domain, but maybe, hopefully, they can be separated in the frequency domain. Otherwise, it's a linear transformation, and some say, well, if it's a linear transformation, there is forward and inverse, there is no gain of information. But that's not completely true in the sense what is separable in one domain may not be separable in the other domain. So extracting certain components that are better separated in the frequency domain than in the space domain. So the 2D Fourier transform in the continuous representation is this. Double integral over xy over all space of the image fxy multiplied with this exponential function, which is now two-dimensional in space and two-dimensional in frequency, a total of 4 dimensions, xy, u, v. The notation typically is u for frequency in the horizontal axis, v for frequency in the vertical axis. Okay? We will see the details later on. Exponential minus j2 pi ux plus vy is separable, ux, vy. and each one has a cosine and a sine in ux and vy. And so if you just take this, 2 pi omega t and 2 pi omega t, or rather, no, 2 pi ft, or just omega t in the time case. Now you have u, and we have 2 pi also included. So u is corresponding to f in frequency in the time domain. So images are functions of space. We will consider 2D functions, x, y. Units of measurement in the image domain are meters, centimeters, usually millimeters and micrometers, but if you're getting images from space and remote sensing, they could be in terms of centimeters or meters. The Fourier domain is cycles per millimeter or cycles per meter or millimeter inverse. Cycles has no dimension, so it is millimeter inverse, like time inverse or hertz in the time domain. Frequency is also expressed as line pairs per millimeter, as I said, but in the frequency domain, when you take the Fourier transform, you would rather use this millimeter inverse. Now, the resolution depends upon the distance between the viewing system and the object. The closer I am to the object, the better I see the details. The farther I go, the details get blurred and the resolution is lost. So it is the angle that the object subtends at my retina that is important. Then cycles per degree of the angle subtended at the retina of the object is what is the frequency unit, not millimeters. Millimeters, the question is where, and what is the distance between the viewer and the object, or the camera and detector and the object. So to take that into account, you convert to degrees of degrees subtended at the detector. We don't use hertz in 2D images. So if you use discrete coordinates, then the DFT is fmn summed over all mn exponential minus j2 pi mk or mnl over n if the image is not square, and divide by mn. That's just direct digitization, digital representation like the DFT. For complete recovery of fmn from fkl, the latter should be computed for k going 0 to m minus 1 and l going 0 to n minus 1. That is, if you have an m by n image, the DFT must be minimum m by n for complete reversal. Otherwise, you lose information if it is less. If it is more, no problem. You get more sampling in the frequency domain, and coming back to the space domain, you get the original. But if you use a lower number of values in the frequency domain, k and l, than the number of sample values in the input, then full recovery is not possible. So the inverse is fmn. Capital F fkl is the Fourier transform summed over k and l exponential plus j2 pi. The same thing, plus. And for all m and n going 0 to m minus 1 and 0 to n minus 1. So this is resolving the given image into a weighted sum of mutually orthogonal exponential or sinusoidal functions. Like here we said, we are resolving a continuous signal in terms of a weighted combination of delta functions. Now, the image fmn is given by a weighted combination of sinusoids, these sinusoids, in 2D with fkl as the weights. So this is resolution. The other one is synthesis. So, sorry, that's synthesis, this is analysis. You would call this analysis, and this you would call synthesis because you are synthesizing the image using sinusoids. Or it is also called resolving the image into a weighted sum of sinusoids. So this is what 1D sinusoids look like. This is the first 8 sine basis functions of 1D DFT, k going 0 to 7. I computed each one using 64 samples. So first is DC, 1 period of sinusoid, 2 periods, and so on. In 2D, this is what the cosine functions look like. Each function was computed using a 64 by 64 matrix. So you have low frequency going high frequency in the vertical direction and in the horizontal direction. So these are sinusoids. And then when you combine them, you get various other patterns in between at other angles. So those are the basis functions of the transform. These are the sine functions. They're similar with a shift. The sine of 0 is 0, so that is black. But otherwise, just for a shift, except for a shift, this and that are the same, but for a shift. When you compute the DFT using FFT, the fast Fourier transform algorithms, nowadays in MATLAB, you can give any number of samples and you get the FFT or the DFT computed using that many samples. But if you want faster computation, depending upon how you compute, it may be advantageous to use a power of 2. That advantage is not much now. But in the 60s and 70s, when FFT first came, and before FFT was published in the 1960s, computing the Fourier transform of even a signal would take a lot of time. And when I was a grad student at IASC, there was only one computer in a big building, and we had to punch cards. Many of you wouldn't have seen punched cards, and take them and deposit them and wait for the output the next day. And taking the Fourier transform of an image was a lot more involved, even with FFT. So imagine in the 60s, before FFT, it used to take a lot more time. And then, with the FFT, having an array of the signal or the input data with the number of samples being 2 to the power of n, 64, 128, 256, 512, 1024, and so on, was an advantage for the FFT algorithm. So then if you have a signal that has 72 samples, you would add zeros at the end, make it 128 for faster computation. So that's called zero padding. And you would do that in images too. Just pad zeros. But then that creates a discontinuity. You have an image that is this much, and I pad zeros and make it that big. There is an edge created that is not present in the image. So that causes some artifacts. So one has to be careful with this. So if you have a square array, n by n, then the forward and inverse Fourier transforms look simpler, and the normalization mn is changed to 1 over n here and 1 over n there, just for convenience. The rest is the same, but 2 pi over n, not m and n separately. So this gives you some convenience in notation. Okay? So a few functions in their Fourier transforms. If you have a rectangle function, fxy equal to a for x between 0 and capital X and y between 0 and capital Y, otherwise 0, then the Fourier transform is axy times a sinc function. You know the gate function and sinc function, we have the same thing, rectangle function and sinc function, but the sinc function now has this. And because the definition of that rectangle was in the first quadrant and not centered, we get a phase factor here. If I were to place the rectangle with the middle center on 0, 0, then that the two exponential factors will not exist. So the exponential factors are the phase components. The Fourier transform for a real image is in general a complex function, so we have to make sure we handle the magnitude and phase, or the real and imaginary parts. An image with even symmetry about the origin will have a real Fourier transform. Like if I were to place the rectangle centered at the origin, then the two exponential factors will not be there. So that is the rect function. The rect function is defined as 1 if modulus of x is less than half and modulus of y is less than half. So half on this side and half on that side, so it's in the middle. The total width is 1. Rect transforms to sinc in 2D. The sinc 2D function is sine pi u over pi u sine pi v over pi v. Separable in u and v. Sinc u, sinc v. Okay? So what do they look like? These are 3 rectangle functions of different width, centered. These are the Fourier transforms. I'll explain that in a moment. This is a sinc function, up and down and up and down. If you take a section of this, it will be a sinc. If you take a section like that, it will be a sinc. And as you make the width of this smaller, the frequency content, higher frequency content will increase. It's becoming smaller and sharper in some way. If it is constant for the whole image, then you only have DC, 1 point in the middle. And if it becomes a single dot, if it is an impulse here, this will be a constant. The Fourier transform in 2D is typically folded. We sometimes do that in 1D also, or we just display the first half. But in 2D, the full Fourier transform is displayed, typically. So the frequency coordinates, when you compute, you may get it with origin there. But for display, we want origin in the middle. Origin is DC, 0, 0 frequency. So we need to take that part and put it here and shuffle so that we get a display with the 0 frequency here, maximum frequency horizontal there, negative maximum frequency minus u over 2, capital V over 2, maximum vertical frequency negative here. So that is shifting or centering the display. So this is what the DFT gives you. But after centering, we get DC here in the middle, which was there. And this is easier to view and interpret. So these are log magnitude of the Fourier transform with shifting. This is without shifting. This is with shifting. So this is maximum horizontal frequency, maximum vertical frequency, positive and negative. You may use this wire mesh display if you like. So the sinc is more clearly seen, but this is magnitude, no negative values. And especially if you want to take log, you take log of magnitude. So that's the rectangle function and the sinc function. If the square is changed to a rectangle, then it is it's a sinc function, all right, but these two sinc functions in the two directions are not the same. So it is longer in this direction. So the period of the sinc function is different in the vertical direction compared to this section, which is shorter, and then that frequency, the spacing between the zeros, what you see there, the black portions, is different. And when you have a bar, a rectangle or a line, then rotation or angle is another issue, another variable. Here it is placed horizontally, placed vertically. It's essentially the same thing turned around, but for some computational variations, because everything is done on a discrete grid with size limitation. But essentially, this, if you rotate this, you rotate that by the same angle. And here we have at 45 degrees, you see that major axis this way and that way. Two sinc functions. Rotation of an image causes a comparable rotation in the frequency domain. But what you need to recognize also is that there is a 90-degree shift in terms of the details in the horizontal and vertical directions in the image domain compared to the frequency domain. I'll show that later on when we get examples of that nature. If you have a circle function which is common in imaging systems, the aperture used is approximated by a circ function. A circ function is defined as having a radius of 1, so it is 1 if r is less than 1, otherwise 0. R is square root of x squared plus y squared. Circular details are better expressed using polar coordinates, where r is root of x squared plus y squared, and then there is an angle function. The Fourier transform of circ is a Bessel function, where nu, this frequency, is expressed in terms of square root of u squared plus v squared. U and v are the horizontal and vertical frequency components in the two-dimensional Fourier transform in the rectangular or Cartesian coordinate system. This is in the polar system. This is a circle on a digital image. So it's not a perfect circle. There are a few inaccuracies there. And this is a Bessel function. But this is all artifact. It's supposed to be just circles going around. Like a sinc function. If you take a cross-section, it looks like a sinc function. This is as wire mesh. If you take a section of this is a two-dimensional section, or rather a one-dimensional section over the full horizontal axis. So it is symmetric, and it is isotropic. So this is isotropic. So you don't need to show the whole thing. So you can take a section, and you don't even have to show this much. Half is enough. So you are showing a radial profile for only positive frequencies. And this is what is normally shown if your imaging system is isotropic in the frequency domain. You can do the same thing for the point spread function too, because that's also isotropic, right? So only half of it is shown, half of a section. But if you want a nice pictorial display, then this would be what you would use, except for the artifacts, because of the discrete representation. I could have blurred it, I didn't do that. So profiles of 2D system transfer functions or modulation transfer functions are commonly shown only for one half of the profile for positive frequencies. It is assumed in that case that the system is isotropic. If it is not isotropic, you must show the full 2D Fourier transform. So here are some examples. I showed this image earlier. This is in the knee joint, we have ligaments connecting the bones. And one of my projects was on the analysis of the structure of the collagen fibers. So collagen fibers run along the length of the ligament. And in this image, a cross-sectional slice was taken, and this is transmission electron microscopy. And in the case of a normal tissue, there is a variation in the thickness of the fibers naturally. In the case of scar tissue that develops after injury, there is not that much of variation of thickness or the diameter of these fibers, which is not good for strength. So we wanted to analyze the distribution of the size or thickness of the collagen fibers. Anyway, these are a bunch of circles. So when they're all similar, the sync pattern can be seen to some extent. Can you see that? This and that. And after that, you can't see. Because there are so many of them, there is interference between them. In this case, there is a mix of thick and thin and medium fibers, so you don't see that sync pattern clearly. Anyway, if you take one of them, you will get a sync pattern. You will get a Bessel pattern. I said sync, it's Bessel. or a circle. These are collagen fibers in scanning electron microscopy, where the ligament is fractured and an electron beam is used to scan the fractured surface. So what you see are ligament fibers, collagen fibers rather, and this is the axis of the ligament, and you have a neat parallel arrangement of the collagen fibers normally. In scar tissue after injury, that organization is not there. It is developing. Eventually the organization changes, and I'll show examples much later. So the Fourier transform shows the angular distribution. Here, there's not much variation in angle. It's not isotropic, but there's no specific pattern over angle as compared to this. You see concentration of energy here. So that shows there are directional components in the image. We saw the rectangle, and when the rectangle is turned, then the Fourier transform shows that axis of concentration of energy. And that is what is happening here. So you can see this. Perpendicular to that is this direction. So all fibers in that direction, there and there, have their Fourier transform components there. If you cut a section there, it's a sinc function. And this, perpendicular to that is this. So all of these fibers, each one of them is a rectangle function. The Fourier transform will be perpendicular to that direction. They're all there. So if I take only this portion, I get only the vertical components. I can do directional filtering and analysis. That is what we did. I'll show you that later. So this is an illustration of the Fourier transform in 2D. Okay? If you have any questions, feel free to ask. We will have more general discussion later. Okay. So there are a few important properties. The kernel function, the basis function, is separable and symmetric. The two-dimensional exponential function can be separated, and the double integral or summation can be separated. So there is an integration or summation on m with this exponential with mk, and then another on n with this exponential on nl. This is the given image. So you can separate the two-dimensional DFT into two one-dimensional DFTs. So one working on the rows and the other on the columns, whichever way you like it, first row and then column, or the other way around. So 1D FFT algorithms are used to get 2D or multidimensional FFTs, Fourier transforms. FML is, you have to take care of the scale factor. If you have 1 over n, you may want that n. Otherwise, if you are scaling later for display, it doesn't matter. So this FMN using NL, sum on n. Take the result of this FML, take that, and apply another DFT on MK using m as the index. You can do this first, and then that doesn't matter. So 1 over n is a factor that you need to check if your FFT algorithm has inside or outside. But if you're scaling using log and so on, it doesn't matter. Parseval's theorem says energy should be conserved, so integral of fxy square should be equal to integral of fuv square. The inverse Fourier transform is the Fourier transform of the conjugate of the frequency domain function, and then the conjugate of that. So forward and inverse Fourier transforms can be computed using the same FFT algorithm. Inverse, you take the conjugate and take the Fourier transform and take the conjugate of that. That becomes the inverse transform. The same in 1D also. The Fourier transform is linear. If you have an image gxy with a linear combination fxy plus eta xy, where eta xy is noise perhaps, then guv is fuv plus eta uv. That's true in all dimensions. Most real-life images have a large portion of the energy concentrated at DC because there's an average brightness. The average of a real-life image is not zero. There's no negative light. So when I take a picture, all the values are positive in terms of the light reflected. But if you have some other image that is somehow scaled or transformed like CT images, there are positive and negative values of Hounsfield unit. But in a regular image, they're all positive pixels, so the average value is high, quite high. In fact, you want a bright image. So that means at the DC in the middle, there is a very large value. And the rest of the values will not be seen clearly, so you take log and suppress that large value. But in any case, DC represents the average value. And higher frequency values are related to edges. Edges, sharp features, and small scale or fine details lead to higher values in the higher frequency components or strength in the higher frequency components. But random noise has a spectrum that is flat, white noise, because the values are uncorrelated. So one may say, well, if I take high frequency, it's only noise, so I'll cut that, use a low-pass filter, and remove all the high-frequency components. But in imaging, in image processing and with real-life images, there is some energy there. Although it is low, if you remove indiscriminately high-frequency components, your picture will be blurred. You remove noise, yes, but you also lose sharpness. So image sharpness translates to high-frequency energy in the frequency domain using the Fourier transform. I should put this away. This is the one. Oh, okay. Sorry, I've been looking at the clock earlier, but now I stopped looking at it. Shall I finish some of this? Just a couple more minutes. The DFT and its inverse are periodic signals. When you sample a signal, there is periodicity in the frequency domain. When you sample the spectrum, there is periodicity in the input domain, time or space. So FKL is FK plus or minus alpha NL. Alpha is some factor, N is a size. So there is repetition. And you can write it in one of the dimensions or both dimensions. The Fourier transform is conjugate symmetric. F minus K minus L is F star KL. Star is conjugation. Magnitude is the same. Phase is negative when you take the negative frequency. If you shift the input image, Fm minus m naught, n minus n naught, the Fourier transform of the original image, FKL, is multiplied with an exponential factor that is related to the shift, Km naught plus L n naught. So that is a shift, phase shift that you encounter in 1D. You would normally see only one of them. Now you see two. So there is a linear shift, phase shift or phase component added. Conversely, if you take Fmn and multiply with this factor, exponential K naught m plus L naught n, the Fourier transform is shifted. So the shifting of the Fourier transform for display can be achieved using multiplication of the input image with an exponential function. But then there is an interesting point about that. I'll talk about that later on. F00 is the average value of the image of DC. There's no current here, but we still call it DC because of electrical engineering. I don't know what computer scientists call it, but anyway, we still call it DC, zero frequency, which is the average value, just integral of fxy because the exponential factor goes away. So that is integral of the image divided by the size of the image, average pixel value.